So we've talked about waves some in general. What we're going to move on to now is sound waves specifically. Okay, and so let's talk for a little bit about just some general ideas with sound waves. So sound waves are a longitudinal wave, which remember means that the waving motion is in the same direction as the motion of the wave itself. Okay, so it's oscillating left and right while traveling horizontally. All right, and what it really is a sound wave is simply a pressure wave. So what we end up having is there's these areas of high pressure followed by areas of low pressure. And so sound waves are ultimately generated from some object vibrating back and forth in the air, all right? And that pushes the air back and forth, creating these areas of high pressure, and then in between there's these areas of low pressure. So that's all that a sound wave is, just a variation in pressure. Two quick characteristics of waves that are specific to sound waves. So with the sound wave, the amplitude of the sound wave determines the volume, all right? So a bigger amplitude means a greater difference in pressure, all right? And that ultimately results in a greater volume. The way I always remember this is if we think about, like with a guitar, an amplifier, okay? An amplifier is a device that increases the sound, increases the amplitude of the wave. The other characteristic that we talk about a lot with sound waves is the frequency. So the frequency of a sound wave is what ultimately determines the pitch. Okay, so a very, very high pitch has a very, very high frequency, whereas a low pitch has a much lower frequency. The human ear can hear a frequency from about 10 hertz, okay, so 10 waves per second, which is a very, very low hum, all the way up to about 20,000 hertz, although as you get older, you tend to lose some of those higher frequencies. All right, like all other waves, the speed of a sound wave depends on the medium itself. The speed of sound in air is about 343 meters per second. That's at room temperature, at atmospheric pressure, at some standard humidity. But all of those things, the pressure, the temperature, the humidity, they're all going to affect that ultimate value. But it's about 343 meters per second, okay? Give or take maybe 20 meters per second. So pretty fast, about a quarter of a mile per second. That speed is going to vary some, and it travels a little bit faster in liquids and even faster in solids. You also often can hear a train coming if you're staying at the train station because the tracks start chirping, and that's because sound travels very quickly and also very effectively through a solid like the metal tracks that it's traveling on. And so you can hear it coming through the tracks before you can see it coming or hear it coming through the sound traveling through the air. We talked about four wave properties before: diffraction, reflection, refraction, and superposition. And all of those are present in sound waves. They're present in any waves. Superposition especially is going to be really, really key when we talk about music. But I want to talk just about a few specifics to sound waves for those four wave properties, the four shun words. So the first property is superposition, the adding together of waves. And so one of the biggest things, or the spots where it comes into play the most, is with harmonics, which we'll talk a lot more about later. But that's just the combining of two sound waves to form a newer, more complex wave. Okay, a lot of times if people are into singing, they'll talk about harmonizing, all right? And that means that two people are singing the same thing at different pitches, at different frequencies, but they sing it in such a way that the frequencies blend together nicely, creating a new, more complex, richer wave through superposition. The other thing we'll talk about some is beats, okay? That's a way that musicians can tune their instruments, okay? And we'll look at what that is a little bit later. But they all involve the blending together of sound waves to form new waves, some of which are pleasant, some of which are unpleasant. Another big one is diffraction. Okay, sound waves spread out going through doors and openings. This is why if you're sitting in the hallway, you can hear a teacher talking through the door, even if there's not a direct line for the sound wave to go from the teacher's mouth to your ears. Okay, those sound waves spread out going through doors, windows, etc., and that's why we're able to hear it, even if there's not a direct line for that wave to travel from the person making the sound to the person hearing the sound. The next one is reflection. The most common example of that would be echoes, okay, sound waves bouncing off of objects and returning to the source. And then we do have refraction with sound waves. We don't experience this too much, but this tends to happen a lot over the water. Sound waves will bend, okay, if you have a difference in the temperature of air. So a lot of times on lakes in the early morning, what you have is you have cool air down near the lake because the lake has kept it cool, but the sun has started to warm the air above. And that causes the sound waves to bend in a curved fashion back down like what we see here. And so what that allows to happen is it allows sound to travel better over the water. So very early in the morning, all those sound waves that are going out from this person, a lot of them are going to bend back down, all right, and refocus in an area, and that allows for sound to travel very, very well, all right, across the water. And so you can be pretty far away from a person having a normal conversation, and someone on the other side of a lake might be able to hear you because of this effect, because of refraction. We're not going to talk too much about that, but you should understand, at least conceptually, what that means. Refraction is just the bending of the wave due to this change in the medium, which changes the speed. All right, so the next thing we're going to talk about is the Doppler effect, but really the best way to talk about the Doppler effect is not to see it, but to hear it. All right, so I'm going to play a quick clip that's going to illustrate the Doppler effect. Now, I bet even though you didn't actually see what was happening, you could tell me exactly what was happening in that situation. That was very clearly a car driving past a person. You can hear that change, okay? When the car actually passes, it goes from a higher pitch to a lower pitch. It goes, okay? So you can hear that change in the horn from a higher pitch to a lower pitch, all right? And so the Doppler effect, all right, is that very thing. All right, so the Doppler effect is the apparent shift in frequency caused by motion between the source of a sound and an observer hearing the sound. All right, and that's why ambulances, cars, etc., sound different. All right, when they pass you, because when they're traveling towards you, there's one frequency that you're hearing. When they're traveling away from you, there's another frequency that you're hearing, and that's why you get that sound that you hear in the clip. So let's listen to it one more time real quick just to hear that shift that occurs when the car passes, and it goes from going towards you to going away from you. That right there is the Doppler effect, that shift in the frequency. So let's talk for a second about why this Doppler effect actually happens. So if we look up here at this fire truck, that fire truck is traveling to the right there. Okay, and we have our observer here listening to the fire truck as it passes and continues traveling to the right. What ends up happening is the fire truck blares its sirens as it's moving to the right, and because it's emitting this sound, all right, so that's showing that pressure wave, that sound wave, because it's emitting that sound and moving in the same direction, what ends up happening is these waves end up getting scrunched together. Okay, because the fire truck makes a sound, all right, and then moves and then makes the next sound, so they end up being closer together than they would be normally. That bunching, okay, of those sound waves ultimately leads to an increased frequency of the sound, okay, because the waves happen more frequently than they would if the truck wasn't moving. And when the truck's going away from the person, we have a similar effect because the sound is emitted, but then the truck moves away before the next wave is emitted. And so that ultimately leads to a decreased frequency, okay? I'm saying that the waves are emitted. What I really mean is one wave front, one peak is emitted. But the truck moves away in the process, and that stretches out and increases the wavelength between the waves, decreasing the frequency. Okay, and we see it here too with the police siren. All right, same basic idea. Behind the police car, the waves are spread out, leading to a lower frequency. In front of it, the waves are bunched together, leading to a higher frequency. So we can mathematically calculate this shift in frequency. And so here's our equation for the Doppler effect. It's the frequency observed is equal to the frequency of the source, right? So the frequency that the source actually emits compared to the frequency that the person or an observer actually hears. So the frequency of the source times this nasty fraction here. So what this fraction says is V plus or minus VO, where V is a constant, the speed of sound, plus or minus the velocity of the observer, and we'll talk about whether it's plus or minus in a second, divided by V, that same constant, 343, plus or minus the velocity of the source. And again, we'll talk about whether it's plus or minus in a second. All right, but that's our equation for the Doppler effect. So how exactly do we decide if it's plus or minus here? There's a lot of different ways of doing this. I think the easiest way is to just think about it conceptually and decide what needs to be done mathematically so that the math matches up with the concept. And here's what I mean by that. We know that whenever the source or the observer, either one could be moving, is moving towards the other, the frequency will increase. Okay? So if I look at my fraction, if it's the observer that's moving, and it could be one or the other, but if it's the observer that's moving, what do I need to do to make it so that the frequency observed is bigger than the frequency of the source, an increased frequency? What I need to do is I need to have a bigger number on top of that fraction. So I'm going to add. If the source is moving towards, though, what do I need to do to make the frequency observed be bigger than the frequency of the source? I need to divide by a smaller number, so it's going to be subtracted on the bottom. And the flip happens when one or the other is moving away. Okay, when the observer is moving away from the source, that's going to result in a lower frequency observed, so I'm going to subtract that velocity of the observer on top. And when the source is moving away from the observer, I want to divide by a bigger number because the frequency observed is going to decrease. And so I'm going to add the velocity of the source on the bottom. All right, we have a quick conceptual question here. So a person is marching and playing an instrument. Maybe it's Mr. Kernahan marching and playing his tuba. And we want to consider the period of time while he's marching towards us. All right. So the first question, how does the person's motion affect the pitch of the note that you hear? Since they're marching towards you, okay, what that is going to do is that's going to cause the waves from their instrument to bunch up. And here you are hearing those waves. You're going to actually hear an increased frequency, all right, and that's going to lead to a higher pitch, all right. So an increased frequency because they're moving towards you. How does it affect the volume that you hear? Volume depends on the amplitude. Doppler effect doesn't tell us anything about the amplitude. There would be no change to the amplitude or the volume, just a change to the frequency and therefore the pitch. All right, so for this problem here, we have a prison break, and we have this prisoner here that's running away from the prison at some velocity. The prison emits a siren with a frequency of 440 hertz, but the prisoner only hears a frequency of 400 hertz, and we want to find his velocity. So we're going to go ahead and first set up our Doppler effect equation. So we can fill in the things we know here. We know the frequency observed is 400. The frequency of the source is that 440. Okay, and then we're going to have our velocity, so 343, the speed of sound, plus or minus, we'll figure that in a second, the velocity of the observer, which is the prisoner, over 343, plus or minus the velocity of the source, which is 0, so then it really doesn't matter what we have. If we think about this conceptually, we know that this motion reduces the frequency, so we want a smaller number on top, which means that there has to be a negative sign. Okay, we can now go ahead and multiply by 343, this number on the bottom, and divide by 440, and so we end up getting 311.8 is equal to 343 minus the velocity of the observer. So the velocity of the observer is just 31.2 meters per second, which is ridiculously fast, but that's what the math works out to be. All right, for this next one here, we have a car driving down the street at 12 meters per second, and the car emits or blows on its horn, which has a frequency of 300 hertz. And we have a runner up ahead traveling away from the car at 4 meters per second. And we want to know what frequency does the runner hear. So we'll set up our Doppler effect equation one more time. So we know the frequency observed is what we're looking for here. The frequency of our source is 300. Times the velocity, the speed of sound, which is 343. We're going to put in the velocity of the observer. I'm just going to leave it as 4 and figure out my signs later. And then 343 and the velocity of the source, which is 12. So let's consider each one of these motions independently. The runner moving away from the source decreases the frequency. So I'm going to subtract that 4 on top. That ultimately will lead to a lower frequency observed. The car, however, moving towards the runner increases the frequency. So I'm also going to subtract on bottom because dividing by a smaller number will increase that frequency. So we consider each motion independently. And we end up getting a frequency observed here of 307 hertz. So a slight shift from the 300 hertz that the source is emitting.